In today's webinar, we're going to cover the purpose of high potential testing, types of high potential test sets, including direct current, power frequency, 50-60 Hz, near power frequency, or resonant sets, and very low frequency, or VLF test sets. We will also cover selecting a test set based on the application, types of tests and their purpose, and measurement errors, environmental effects on readings, and finally, safety. In electrical testing, a high potential test or pressure test, dielectric withstand, or high-pot test is performed on a component or product to determine the effectiveness of its insulation. The test may be between mutually insulated sections of a part or energized parts and ground. The test is a means to qualify a device's ability to operate safely during rated electrical conditions. If the current through a device under test is less than a specified limit at the required test potential and time duration, the device meets the dielectric withstand requirement. A high potential test may be done as a factory test on new equipment or an apparatus already in service as a routine maintenance test. Voltage withstand testing is done with a high voltage source and voltage and current meters. A single instrument called a high-pot or dielectric test set is often used to perform this test. It applies the necessary voltage to a device and monitors leakage current. The current can trip a fault indicator, and the tester has output overload protection. The test voltage may be either direct current or alternating current at power frequency or other frequencies like resonant frequency, typically 30 to 300 Hz, or very low frequency, ranging from 0.01 Hz to 0.1 Hz. The maximum voltage is given in the test standard for the device under test. The duration of the test is dependent on the type of test, installation, acceptance, maintenance, the device under test, and various industry guidelines. Now, let's talk a little bit about the types of high potential test equipment. As stated, the test voltage may be either direct current, alternating current at power frequency, alternating current at resonant frequencies, alternating current at very low frequency. And this can be further broken down into categories: power frequency sinusoidal voltage sources, near power frequency or NPF sinusoidal voltage sources, or alternative voltage sources of various wave shape. Okay, I know what you're probably thinking. Why so many types of high potential test equipment and voltage sources? Well, let's consider the wide variety of products requiring high potential testing. We have rotating machines, power cables, bushings, instrument transformers, lightning arresters, personal protective equipment, switchgear, air, gas, or oil, transformers or shunt reactors, power capacitors, and circuit breakers, just to mention a few. Okay, now that's a lot of products, but you're probably still asking, why not test them all with AC power frequency? After all, electrical transmission and distribution occur at power frequency. AC voltage testing at power frequencies of 50 and 60 Hz is typically conducted by the manufacturer, and it stresses the insulation similarly to normal field operation. Portable AC high potential power frequency variety test sets are used worldwide For testing devices such as vacuum bottles, switchgear, reclosures, circuit breakers, etc. So, once again, why so many types of high potential test equipment? Well, power frequency testing being used on devices with high capacitance, like power cables and large rotating machines, has several disadvantages in a field application. At higher voltage levels, the test set requires heavy, bulky, and expensive transformers. These transformers are typically better suited for factory testing by the manufacturer. The reason for large transformers when referring to items like power cables has to do with the capacitance of the load being tested. Capacitive reactance, or X sub C, changes as a function of frequency, as seen in the formula X sub C equals 1 divided by 2 pi Fc, where F is the frequency of the test voltage and C is the capacitance under test. Therefore, if we're testing a 15 kV rated cable of approximately 10,000 feet, the capacitance would probably be around 1 microfarad. Based on the formula, the capacitive reactance at 60 Hz will calculate out to be 2,654 ohms. Now, if we were to apply the IEEE recommended 22 kV test voltage, it would require a power supply rated for 8.3 amps or 183 kVA. Now, we can find this by simply taking the 22,000 volts and dividing it by the capacitive reactance, 2,654 ohms, and we see that we would get 8.3 amps. To find the VA, simply take the 22,000 times the 8.3 amps, and that's where we get the 183 kVA transformer. A bit large in a field application. All right, well, now that we better understand the disadvantage of AC power frequency testing of high capacitive devices in a field application, what are our choices for a more practical field instrument? For years, high voltage DC testing has been the traditionally accepted method for judging the serviceability of high capacitive devices such as medium voltage cables. Direct current tests have worked well for conducting high potential and condition assessment tests on paper insulated lead covered or PILC cable. When plastic insulated cables were first introduced in the 1960s, DC continued to be the preferred method. As time moved on, plastic insulated cables became more abundant and began showing effects of service age. Direct current continued to be the dominant test, but concerns began to grow over the effectiveness of this test. In the early 1990s, reports started to surface indicating that DC high potential testing could be the blame for latent damage experienced by extruded medium voltage cable insulation, particularly cross-linked polyethylene. After receiving these reports, the Electrical Power Research Institute, EPRI, funded a study relating to cross-linked polyethylene XLPE cables. This study, the EPRI report TR-101245, yielded the following conclusions regarding XLPE cable. 1. The report concluded DC high potential testing of field age cable reduces its life. Secondly, DC high potential testing is ineffective as a maintenance tool. And finally, the report concluded DC high potential testing before energizing new medium voltage cable does not cause any reduction in cable life. The EPRI report also provides the following recommendations. To be safe, it is recommended not to conduct any DC testing at 40 kV or corresponding to a stress of 228 volts per mil on crosslink polyethylene insulated cable in service. And DC testing can be done up to 55 kV in the field on an unaged cable, never been in service. The International Electrical Testing Association, or NETA, maintenance testing specifications for shielded cables, medium and high voltage, provide options for withstand testing of cables. One of the options provided is DC withstand testing. The specification clearly states that the application of DC is for extruded dielectric cables of less than 5 years in service and references Table 100.6.1. Now, since laminated dielectric shielded power cables age differently from extruded dielectrics, they do not experience the ill effects of high voltage DC. They can be tested with DC at any stage of their life, and we see this reflected in the NETA Table 100.6.2. Continuing on our topic of when is it acceptable to use high voltage DC, let's talk a little bit about vacuum interrupters or vacuum bottles. Vacuum circuit breakers have for many years included a label to advise users of the potential for emission of X radiation under certain conditions. Also, the American National Standards Institute, ANSI, established an exposure limit when qualifying vacuum interrupters. This is defined in ANSI C37.85, alternating current high voltage power vacuum interrupters, safety requirements for X radiation limits. The emission limit established in ANSI C37.85 assume that the high potential tests are conducted at the field test voltage allowed in the relevant apparatus standards. The field test voltage is 75% of the factory test on new equipment. This information becomes important when testing vacuum integrity with a DC high potential test set. You need to know your test set and its design. DC high potential test equipment that employs unfiltered half-wave rectifiers must not be used. These test sets often produce peak voltages much higher than the test set indicates. Therefore, the actual voltage applied to the vacuum interrupter by such test sets will be significantly higher than the voltage for which the vacuum interrupter is qualified. This in turn has two unfortunate consequences. First, and most important, the level of X radiation emission may be much higher than that which occurs at the correct test voltage. And second, the leakage current during the test may be so high that test personnel may conclude that the vacuum interrupter has lost the vacuum when in actuality it is not. For these reasons, DC high potential test devices using half-wave rectification must not be used to test vacuum interrupters. Now, under certain conditions, a DC high potential test may make a good interrupter appear bad. For example, when a DC test voltage is used, a high field emission current from a microscopic sharp spot on one interrupter contact can be misinterpreted as a sign of a vacuum interrupter filled with air. To avoid a misinterpreted test result with DC, retest the open interrupter at the opposite polarity if a vacuum interrupter appears to fail the DC high potential test. A bad interrupter filled with air will have a similarly high leakage current in both polarities. A good interrupter with a good vacuum level will still have a high leakage current, but this will generally be in only one polarity. Such an interrupter usually has a tiny sharp spot on one contact that produces a high field emission current when the sharp spot is on a cathode but not on an anode. In addition, such an interrupter would typically withstand the required AC voltage, which is the definitive test of its vacuum integrity. The NETA maintenance testing specification lists dielectric withstand as an optional test for medium voltage vacuum circuit breakers, and both AC and DC voltage values are given in the reference table 100.19. However, as we learned, care should be taken when using DC voltage and ensuring that your test set is a full wave rectified test set and not a half wave rectified unfiltered test set. Let's explore some more of the NETA tables in order to determine when is it acceptable to use high voltage DC for testing. Now, in NETA table 100.9, Instrument Transformer Dielectric Tests Field Maintenance, we see a column for DC test voltages. We also see some very important notes on the use of DC testing. 1. Periodic DC potential tests are not recommended for transformers rated higher than 34.5 kV. And 2. Under some conditions, transformers may be subjected to periodic insulation tests using direct voltage. In such cases, the test direct voltage should not exceed the original factory acceptance test RMS alternating voltage. In NETA table 100.16, high potential test voltage for periodic test of line sectionalizers, we see columns for both AC and DC test voltages. DC test voltages are for a duration of 15 minutes. In NETA table 100.17, metal enclosed bus dielectric withstand test voltages, we see a column for DC test voltages, but once again, we see some very important notes regarding the use of the DC test voltage. The presence of the column headed DC does not imply any requirement for a DC withstand test on AC equipment. This column is given as a reference only for those using DC tests and represents values believed to be appropriate and approximately equivalent to the corresponding power frequency withstand test values specified for each class of bus. Direct current withstand tests are recommended for flexible bus to avoid the loss of insulation life that may result from the dielectric heating that occurs with rated frequency withstand testing. And because of the variable voltage distribution encountered when making DC withstand tests, and variances in leakage currents associated with various insulation systems, the manufacturer should be consulted for recommendations before applying DC withstand tests to this equipment. In NETA Table 100.2, switchgear withstand test voltages, we see a column for DC test voltages, but once again, we see some very important notes regarding the use of DC voltage. Let's take a look at note number 2. The column headed DC is given as a reference only for those using DC tests to verify the integrity of connected cable installations without disconnecting the cable from the switchgear. It represents values believed to be appropriate and approximately equivalent to the corresponding power frequency withstand test values specified for voltage rating of switchgear. The presence of this column in no way implies any requirement for a DC withstand test on AC equipment, or that a DC withstand test represents an acceptable alternative to the power frequency withstand test specified in these specifications, either for design tests, production tests, conformance tests, or field tests. When making DC tests, the voltage should be raised to the test value in discrete steps and held for a period of 1 minute. In Note 3, it states, because of the variable voltage distribution encountered when making DC withstand tests, the manufacturer should be contacted for recommendations before applying DC withstand tests to the switchgear. Voltage transformers above 34.5 kV should be disconnected when testing with DC. And then the note refers you to IEEE C57.13 2015, the IEEE standard requirements for instrument transformers, and references paragraph 8.5 of that standard. Let's take a moment now to talk about types of high potential tests. Overpotential tests focus on assessing the dielectric strength of insulation and are conducted at specified voltages that equal or exceed the device's operating level. The voltage level and duration of these tests may vary depending on the age of the insulation. Overpotential tests are typically divided into 2 categories: installation and acceptance testing, which pertains to new insulation, the maintenance testing, which applies to service-aged insulation. One of the types of tests that we'll take a look at is the DC step voltage test. The HiPOT step voltage test is recommended for motors operating at RMS voltages of 2,300 volts or higher. It can be conducted on motors at any operating voltage when more detailed information than a 1-minute HiPOT test is required. In a HiPOT step voltage test, the voltage is usually raised in equal steps. At each step, the voltage and measured current are recorded after 1 minute per IEEE 95. The number of steps is determined by the test operator and can be anything from 5 to 30 or more voltage steps. 10 steps are common for medium voltage motors. More steps may be used for high voltage motors. HiPOT step voltage tests provide much more information than a 1-minute HiPOT test because the data is recorded as the voltage is raised. By charting a current versus voltage curve, one can usually tell if the leakage current is mainly due to contamination, dirty windings, or due to a breakdown of the insulation. Here we see good test results on a 3,300 volt motor with test voltage stepping up to 7,600 volts. Good windings will have a curve that is more or less a straight line as shown in the graph. The current depends on how contaminated the windings are. And in this case, the current and contamination level is low with a total leakage current of less than 1.4 microamps. Here we see acceptable results on a 4,000 volt motor with test voltage stepping up to 9,000 volts. 4 10-point step voltage tests were done over time. The two bottom curves from the first two tests are very good. The red and blue curves from the next two tests show minor acceleration in the current. But the maximum current is still relatively low at 11 microamps, and the acceleration starts above 7,000 volts, significantly above peak operating voltage. The elevated total leakage is mainly due to increasing winding surface contamination, including moisture, judging from the previous tests. If the acceleration in the current was significant and the blue line moved more toward vertical, it would indicate a breakdown of the insulation. Now, this test on a 6,000 volt motor with test voltage stepping up to 11,700 volts is concerning. The test represented by the blue curve did not shut the test down early because the maximum current at about 25 microamps did not reach the total leakage current limit, and the acceleration of the current was not high enough to exceed the chosen trip limit of 2, current rate of change between voltage steps. However, the accelerating leakage current and the current level at the end of the test indicates weak insulation that is starting to break down. The current acceleration starts slowly at about 6,000 volts, so the motor condition is concerning, but still okay. No arc was detected during the test since that would have shut off the test early. With a lower trip limit, the test would have been shut off before reaching the full test voltage. Now, this test on a 4,160 volt motor with test voltages stepping up to 9,320 volts definitely shows us a problem. In this test, there was a sudden breakdown of the insulation between about 5.6 and 6.5 kV, and the test is shut down at the end of step 7 at about 6,500 volts because the acceleration in the measured current exceeded the trip limit from step 6 to step 7. With rapid acceleration of the current, the chance of an arc increases significantly, but that did not occur here. The breakdown is happening around the peak operating voltage of 5,882 volts. With this result, the motor may be able to operate for a while, but it is on its way to a complete breakdown. In general, any deviation from a smooth curve should be viewed as a potential warning. A very abrupt drop in conduction current is rarely found, but when it occurs above the peak operating voltage for the winding, it may indicate approaching insulation failure. Mechanical abrasion and cracking may cause abrupt and unexpected insulation breakdown. All right. Let's move back onto our topic now of optional voltage sources, and we'll pick up with the near power frequency voltage source. Near power frequency sinusoidal voltage sources can replicate the waveform of the operating voltage in the device under test system and allow for increased voltage magnitude beyond the normal operating levels. For the purpose of this webinar, near power frequency voltage sources are defined as sources that generate a sine wave with a frequency range of 20 Hz to 300 Hz when connected to the device under investigation. Specialized test supplies allow the voltage to be varied and are fault current limited to help minimize any damage in the event of insulation breakdown during testing. Series resonant test sets are generally used to keep the size and weight suitable for field transportation. The two types of power frequency series resonant test systems commercially available for field tests are as follows: the frequency-tuned resonant circuits, or FTRCs, and the inductively tuned resonant circuits, or ITRCs. Frequency-tuned resonant circuit test systems have no moving parts and may be smaller than inductively tuned resonant circuit test sets for test power levels above 8 MVA. Inductively tuned resonant circuit test sets utilize variable inductors that tune with a movable ferrous core. These systems contain moving parts that can require maintenance and adjustment over time. Systems are generally limited to 15 MVA in single units at any voltage rating. Multiple units may be run in series or parallel for increased voltage or current. The NETA maintenance testing specification for shielded cables medium and high voltage provide options for withstand testing of cables. One of the options provided is dielectric withstand testing at power frequencies ranging from 20 Hz to 300 Hz. This test lasts either 15 or 60 minutes at the maximum voltage applied to individual or grouped cables, following the manufacturer's published data. In cases where the manufacturer's data is not available, voltage values can be found in the NETA table 100.6.5. The next type of voltage source that we will discuss is the alternative voltage sources. For the purpose of this webinar, alternative voltage sources refer to field testing supplies generating voltages that may be non-sinusoidal, have frequencies other than near power frequency, or are pulsed and not continuous. In the category of alternative voltage sources, let's start with the very low frequency, or VLF. Modern sinusoidal VLF sources generally provide load-independent, smooth, sinusoidal AC test voltages at a nominal frequency of 0.1 Hz. Cosine rectangular VLF has a frequency of 0.1 Hz, but the waveform has a fast, near power frequency polarity reversal followed by a DC plateau of approximately 5 seconds. All right, so what makes VLF an attractive option for testing high capacitive devices in a field application? And why is a VLF test set smaller than a power frequency test set or a near power frequency test set? Well, once again, we have to look at the capacitance of the device under test, and we have to look at the capacitive reactance. So, once again, X sub C equals 1 divided by 2 pi FC, where F is the frequency of the test voltage and C is the capacitance under test. Therefore, Going back to our example, if we're testing a 15,000 volt rated cable at approximately 10,000 feet in length, the capacitance would be around 1 microfarad. Based on the formula, the capacitive reactance at 0.1 Hertz VLF would calculate out to be 1.6 megohms. Now, based on this capacitive reactance, the same 22,000 volts discussed earlier would now only draw 14 milliamps or 303 VA. Therefore, the size, weight, and portability of the power supply becomes very convenient for field use. Commercially available very low frequency or VLF voltage sources are lighter and smaller than near power frequency voltage sources. Unlike DC voltage sources, the VLF waveform has regular polarity changes and is unlikely to produce harmful space charges in the extruded dielectric. The VLF voltage shapes and procedures for withstand and diagnostic testing of medium voltage cables are given in the IEEE standard 400.2. VLF-based testing is also included in the NETA testing specifications. VLF withstand test voltages for sinusoidal and cosine rectangular waveforms are given in Table 3 of the IEEE standard 400.2 2013, Guide for Field Testing of Shielded Power Cable Systems Using Very Low Frequency. Regarding the duration of the test, IEEE standard 400.2 states, the recommended minimum testing time for a simple withstand test on aged cable circuits is 30 minutes at 0.1 Hertz. If a circuit is considered important, example feeder cables, then consideration should be given to extending the testing time to 60 minutes at 0.1 Hertz. The recommended minimum testing time for an installation and/or acceptance withstand test on new cable circuits is 60 minutes at 0.1 Hertz. A test time within the range of 15 to 30 minutes may be considered if monitored characteristics remain stable for at least 15 minutes and no failure occurs. Monitored withstand testing evaluates the impact of voltage application on the cable system. This testing can help identify potential defects or failure locations that may not manifest during the test. While the IEEE 400.2 does not specify values for leakage current, it does provide tan delta figures of merit that can be utilized for condition assessment during a monitored withstand test. See our webinar, Understanding Tangent Delta Testing of Medium Voltage Power Cables, for more information on tan delta testing. The NETA maintenance testing specifications for shielded cables, medium and high voltage, provide options for withstand testing of cables. One option is a very low frequency or VLF dielectric withstand test. NETA Table 100.6.3 is an adaptation of Table 3 from the IEEE standard 400.2 2013. The recommended duration of the test is a minimum of 30 minutes without the occurrence of a failure. If the cable is deemed critical, a 60-minute withstand test is recommended. If a failure occurs, the test should be fully repeated after making the necessary repairs. All right, let's look at yet another alternative voltage source. Let's take a look at the damped alternating current or DAC voltage source. Damped alternating current or DAC voltage sources are lighter in weight and have lower power requirements than near power frequency excitation sources. IEEE standard 400.4 addresses DAC voltage testing in the near power frequency range from 20 Hz to 500 Hz. Damped alternating current voltages are generated by charging the cable system under test to a predetermined voltage level, then discharging the test object's capacitance through suitable inductance. During the charging stage, the test object is subjected to a continuously increasing ramp voltage. During the discharging stage, the test object experiences a damped oscillating wave. A withstand test using DAC voltage is based on the application of a defined number of DAC excitations at a selected voltage level that is generally higher than the rated voltage. DAC testing can be applied to all cables and accessory types, and it is based on the insulation breakdown, no breakdown outcome. In conducting a non-monitored withstand test, no information is gained about the test's effects on the insulation system. And once again, the NETA maintenance testing specifications for shielded cables specify optional tests for medium and high voltage cables. Although NETA does not classify the damped alternating current or DAC method as a withstand test, it is mentioned in the offline partial discharge testing section, specifically in NETA Table 100.6.4, which references the DAC voltage source. All right, let's move away from the voltage sources and let's talk about measurement errors and environmental effects on readings that are obtained during high potential testing. As we learned in our Mastering Insulation Resistance Testing webinar, insulation resistance is very much affected by temperature. So adjusting the test results to a standard temperature is important. Fortunately, most high potential tests focus primarily on whether the outcome is a pass or a failure, rather than measuring leakage current or other values. Monitored withstand testing evaluates the impact of voltage application on the cable system. As stated earlier, this testing can help identify potential defects or failure locations that may not manifest during the test itself. We're typically more concerned with the stability of the readings during the test period rather than their absolute values. Now, cable preparation and setup is important if we want to obtain accurate measurements. Capacitively coupled or induced currents can cause inaccuracies in leakage current readings. For instance, if a cable termination is positioned too close to a grounded surface, current may be induced or coupled onto the ground plane. This can affect your test results, leading to readings that are higher than the actual values. High humidity and moisture can promote surface leakage current. This will result in higher than normal leakage current readings. A guard function can be used to control this error. The guard is a shunt circuit that diverts surface leakage current around the measurement function. If parallel leakage paths exist, a guard connection will eliminate those from the measurement and give a more precise reading of the leakage between the remaining elements. If a guard cannot be used, bagging the terminations or wrapping with cellophane has been attempted to reduce the surface tracking. Now let's look at test area safety. When performing electrical testing, we temporarily energize the circuit with a test potential or voltage. The device under test is now energized and presents an electric shock hazard. Energy control safe work practices must be followed to mitigate this hazard. If testing cables or sections of a bus run, electrical shock approach boundaries must be established at both ends of the cable or bus run to create a safe test area for workers. Also, an energized cable can create capacitive coupling to adjacent cable phases. To prevent capacitive coupling, cable phases that are not energized or tested must remain grounded. So, let's talk about electric shock. A shock hazard is a source of possible injury or damage to health associated with currents through the body caused by contact with or approach to energized electrical conductors or circuit parts. Current through the body causes electric shock or electrocution. The potential difference a person may take between the conductive part of equipment or between the equipment and the ground is essential because this voltage forces current through the body according to Ohm's law. Therefore, current through the body increases with lower resistance and contact voltage. Extensive research on the effects of short-duration shocks or current through the human body was conducted by Dalziel at the University of California, Berkeley, in the 1960s. The maximum safe body current for short periods of time is given by Dalziel's equation and is an inverse function of time. Higher currents are permitted for shorter periods of time. The formula states I sub k equals k divided by square root of t, where I sub k is the maximum safe body current in milliamps, t equals the shock duration, and k is the factor for body weight. Now, looking at our table, at current levels as low as 5 milliamps, slight shock is felt, not necessarily painful, but disturbing. Average individuals can let go. However, strong involuntary reactions to shock in this range may lead to injuries. Now, did you know that most DC insulation resistance test sets, such as megometers, offer output currents of 3 to 5 milliamps? Now, let's take a look at 100 milliamps to 2000 milliamps. In this current range, ventricular fibrillation, the uneven, uncoordinated pumping of the heart, muscular contraction, and nerve damage begins to occur. Death becomes likely. Now, did you know that most of your high potential test sets offer output currents of 100 milliamps to 300 milliamps? Now that we're more aware of shock hazards, let's discuss the safe limits of the approach. As we should have learned during our electrical theory classes, energized circuits or circuit parts produce electrostatic fields. These fields are created by voltage, and the two have a causal relationship, which means that the higher the voltage, the greater the electric field. Any circuit interaction within these fields can lead to electric field induction, also known as capacitive coupling. Electric field induction generates voltages or currents to the ground or both in a conductive object or electric circuit by time-varying electric fields. Since these fields have a causal relationship with voltage, approach boundaries for safety have the same relationship. Higher voltages require greater distances for safety. Remember, You don't necessarily need to come in contact with those energized circuits or parts for them to arc across and give you a shock. The NFPA 70E, Standard for Electrical Safety in the Workplace, defines two approach distances based on voltage: the limited approach and the restricted approach. Let's start with limited approach. An approach limit at a distance from an exposed energized electrical conductor or circuit part within which a shock hazard exists. This boundary is determined based on the nominal phase-to-phase voltage of the energized conductor or circuit part. Unless needed, no unqualified person shall be permitted to approach nearer than the limited approach boundary. The restricted approach. This is an approach limit at a distance from an exposed energized electrical conductor or circuit part within which there is an increased likelihood of electric shock due to electrical arc over combined with inadvertent movement. This boundary is determined based on the nominal phase-to-phase voltage of the energized conductor or circuit part. These boundaries, as used in the NFPA 70E, establish safe distances and awareness when working around energized circuits or circuit parts. They can also assist us in establishing a safe test area when we apply test voltages to equipment. Now, let's look at some key safe work practices when applying test voltages. First, obtain and review up-to-date drawings and prints of all circuits to be tested. If up-to-date drawings and prints are not available, circuits must be traced out and documented prior to applying temporary voltages. The temporary application of voltage cannot proceed until the circuit path, potential backfeeds, affected gear, and circuit access areas are known and factored into the shock hazard assessment and temporary energy control plan. When applying voltage to a circuit, you must treat all parts, such as a transformer bushing, as energized. You must establish limited and restricted approach distances based on the applied voltage. When testing circuits, you must first verify where the voltage is going. For example, verify both ends of a cable. You must know the circuit path 100% prior to applying energy. Before the test, you must barricade all access points. In high traffic areas, barricades may not be enough to keep people out safely, and an attendant should watch all access points. And that concludes our webinar for today. If you like this content, please make sure that you subscribe, hit the like button, ring the bell to be notified of more content as we post it. Again, this all helps our channel, supports our channel, and again, definitely helps me put together the content. So if you like what we're doing, please hit that subscribe, hit that bell, hit that like. All right, until next month, be safe out there.